All right, let's dive right in. Today, we're going straight to the cellular level to really get a handle on the origins of human development. We're going to look at two absolutely critical processes, mitosis and meiosis. And then we'll see how tiny errors in this incredible molecular dance can lead to some of the most significant chromosomal abnormalities we see in the clinic. So let's get started.
Here's our game plan. First, we'll cover mitosis, which is basically the engine of growth. Then we'll switch gears to meiosis and see how it shuffles the genetic deck. After that, we're jumping into the clinical side of things, the real-world impact of chromosomal problems. And finally, we'll break down two of the main ways things can go wrong, non-disjunction and translocations.
Okay, first up, mitosis. You can think of this as the fundamental process that literally builds us. It's how we go from a single zygote to a body with trillions of cells. But it's not just for growth, right? It's also the same mechanism that repairs our tissues throughout our entire lives. Understanding this is key to everything from how a cut heals to the development of cancer.
So what's the big idea with mitosis? Well, it all comes down to one word: fidelity. It is all about making perfect genetic copies. You start with one diploid cell, a regular body cell, and you end up with two daughter cells that are exact clones. Each one gets the full set of 46 chromosomes, neatly organized into 23 pairs. This ensures every new cell has the complete, correct genetic blueprint.
This image gives us a great play-by-play of the stages. Now, you probably know these phases already, but it's really important to remember that each step is a potential point of failure. Look at the alignment in metaphase, for example, where all the chromosomes line up in the middle. That moment is an absolutely critical checkpoint. If those sister chromatids don't pull apart perfectly during anaphase, you can end up with aneuploidy in those cells, which, as you know, is a hallmark of many cancers.
So to wrap up mitosis, the outcome is simple, but it's also profound. One cell becomes two. These two new cells are perfect genetic copies of the original, and that all-important chromosome number, 46, is maintained. It's because of this process that an embryo can grow and our bodies can repair tissues like skin and bone. It's truly fundamental.
Okay, let's shift gears to meiosis. Now, if mitosis was all about making identical copies for growth and repair, meiosis is all about creating genetic variety for reproduction. This is a highly specialized process, and it only happens in our germline, the cells that become sperm and eggs to form the next generation.
You see, meiosis isn't a one-and-done deal. It's a two-part process. There are two separate divisions, meiosis 1 and meiosis 2. And the whole point? To cut the chromosome number in half, taking it from the diploid number of 46 down to the haploid number of 23. This step is absolutely non-negotiable for sexual reproduction. If it didn't happen, the chromosome number would just double with every generation, which is completely incompatible with life.
And this slide right here, this shows what is, frankly, the most remarkable event in all of meiosis: crossover. During meiosis I, the homologous chromosomes, so one you got from your mom and one from your dad, they pair up nice and close, and as you can see, they literally exchange segments of their DNA. They swap pieces. This creates brand new, unique combinations of genes that didn't exist in either of your parents. This is one of the main engines of human genetic diversity. That little X-shaped point where they connect and trade info, it has a specific name: the chiasma. That's where all the magic happens. And this isn't some rare one-off event either. On average, we're talking about 30 to 40 of these crossovers happening every single time a germ cell goes through meiosis. The function is crystal clear: to shuffle the genetic deck and make sure that every single sperm or egg cell is genetically unique.
So at the end of the day, what are the big results of meiosis? Well, there are two huge ones. First, it massively boosts genetic variability, thanks to both that crossover we just saw and the random way chromosomes get sorted. And second, it produces haploid gametes. Each sperm and egg gets just 23 chromosomes. This is so important because when they finally unite at fertilization, boom, the diploid number of 46 is perfectly restored, creating a brand new, genetically unique person.
So we've seen the beautiful, precise choreography of how these processes are supposed to work. Now let's turn to the clinical side of things. The precision needed here is just staggering, and when errors do happen, the consequences can be incredibly profound, affecting development from the very first moments of life.
Okay, get ready for this number, because it is truly sobering. It's estimated that a full 50%, half, of all conceptions end in spontaneous abortion. Many of these happen before a pregnancy is even detected.
It just highlights how incredibly fragile early development is, and it points to a very high rate of major underlying errors. So, what's driving such a high rate of loss? Well, it turns out that an estimated 25% of all conceptuous, that's 1 in every 4, has a major chromosomal defect. These kinds of defects are often simply incompatible with life, and they're a direct cause of that high rate of spontaneous abortion we just talked about. Now, for the pregnancies that do continue to term, chromosomal abnormalities are still a leading cause of major birth defects, making up about 10% of cases. And you can see from this chart, single gene mutations are right there too, as another major contributor. Together, these genetic mistakes are the main reason for many of the congenital malformations you're going to encounter in your clinical practice. All right, let's get specific about what actually goes wrong. We're going to start with one of the most common types of errors, non-disjunction. This is just a fancy term for the failure of chromosomes to separate properly during cell division. When this happens, you end up with daughter cells that have the wrong number of chromosomes. Before we go any further, we need to get our vocabulary straight. Euploid just means a normal, correct chromosome count, like our diploid number of 46. Aneuploid is the opposite. It's the term for any number that's not normal. This usually shows up as either a trisomy, which means there's one extra chromosome, or a monosomy, where one chromosome is missing entirely. This diagram is perfect for showing exactly how non-disjunction happens. So look at panel A on the left. That's normal meiosis, the ideal outcome, producing 4 normal gametes. But in panel B, the homologous chromosomes fail to separate back in meiosis I. This type of error, by the way, is the one that increases with maternal age. And look at the result. All 4 of the final gametes are abnormal. They're aneuploid. Now look at panel C. Here, the error happens later, in meiosis II, when the sister chromatids fail to pull apart. The result this time? 2 normal gametes and 2 abnormal ones. Now, here's a really important clinical distinction. When the non-disjunction happens matters a lot. If it happens during meiosis in a sperm or egg cell, then every single cell of the embryo that's created will have the wrong chromosome number. This is what leads to a full-blown syndrome. But if the error happens later during mitosis in the developing embryo, it can lead to something called mosaicism, where the person has a mix of normal and abnormal cells. This often results in a milder or more varied clinical picture. Okay, so we've talked about errors in chromosome number, but you can also have errors in chromosome structure. This brings us to our last topic, translocations. This is what happens when chromosomes break and the broken pieces get reattached to the wrong chromosomes.
There are really 2 main types to know. First, there's a balanced translocation. Here, pieces of chromosomes have been swapped, but no important genetic information has actually been lost. The person with this is usually totally fine, phenotypically normal. The problem is they're at a higher risk of producing unbalanced gametes themselves. Then you have unbalanced translocations. This is where genetic material is actually lost or gained in the swap, and this almost always leads to an abnormal phenotype and clinical problems.
And here is a classic clinical example you will absolutely see. While most cases of Down syndrome are caused by that trisomy 21 from meiotic non-disjunction, a small number of cases are actually caused by a specific type of translocation. In this situation, the long arm of chromosome 21 breaks off and attaches to chromosome 14. If an individual inherits this combined chromosome plus a normal chromosome 21 from each parent, they effectively have 3 copies of that critical genetic material from chromosome 21, which leads to the clinical features of Down syndrome. So we've walked through the incredibly complex choreography of mitosis and meiosis, and we've seen the serious consequences when things go wrong. It really leaves us with a final massive question, doesn't it? How do these microscopic events, a single chromosome that fails to separate, a tiny piece of DNA that ends up in the wrong spot, translate into the vast, complex spectrum of human health and disease? Understanding that connection, well, that's at the very heart of medicine.
All right, today we are diving deep into the very foundation of human development, the genetic blueprint itself. We're going to explore what happens when that blueprint has an error, from something as big as a whole misplaced chromosome all the way down to a tiny deletion. This is a really detailed look at the major genetic and chromosomal abnormalities in embryology, and we'll be zeroing in on the mechanisms and clinical presentations that are just so essential for diagnosis and patient care.
So here's our roadmap. We're going to start with the most common trisomy out there, Down syndrome. Then we'll pivot to aneuploidies of the sex chromosomes. After that, we'll get into structural issues like deletions and microdeletions, and that's where we'll hit the fascinating concept of imprinting. We'll wrap it all up with fragile sites and single gene mutations before a rapid-fire, high-yield review to make sure it all sticks. So let's get right into it. First up, the one you've probably heard of the most, trisomy 21, which of course results in Down syndrome. It's a classic example of what we call aneuploidy, which is really just a fancy way of saying a cell has an abnormal number of chromosomes. In this case, as the name suggests, the problem is one extra copy of chromosome 21. Now take a look at this. This is a human karyotype, which is basically a visual map of a person's chromosomes, all laid out and organized. And what's crucial here is if you look at position 21, you can see it plain as day. There are 3 copies of the chromosome instead of the usual 2. This single extra chromosome is the fundamental genetic cause of everything we see in Down syndrome.
So you might be wondering, how does this actually happen? Well, this chart breaks it down perfectly. The vast majority of the time, we're talking 95% of cases, it's due to a full trisomy 21. This is usually caused by something called meiotic non-disjunction, an error where chromosomes just fail to separate correctly when an egg or sperm is being formed. Now, a much smaller slice of the pie, about 4%, is due to something called an unbalanced translocation, where a piece of chromosome 21 breaks off and attaches to another chromosome. And then you have just 1% resulting from mosaicism, which is where the error happens after fertilization, leading to a mix of normal and affected cells in the body.
And this image right here does a brilliant job of showing how that one genetic change translates into a recognizable clinical phenotype. You can see the classic craniofacial features, right? The upward slanting eyes, a flattened face and nose, and small ears. Other key signs that you'll look for are a single palmar crease on the hand, just one line going straight across, decreased muscle tone, or what we call hypotonia at birth, and often widely separated first and second toes. But it's not just about the physical traits. There are significant medical comorbidities that go along with it, including intellectual disability, congenital heart defects, and a much higher risk for things like leukemia and thyroid issues. Now, for clinical practice, probably the most crucial point to remember is the strong correlation with maternal age. Just look at these numbers. The incidence jumps dramatically to 1 in 300 by age 35, and it skyrockets all the way up to 1 in 100 by the time a woman is 40. That's a huge deal.
Okay, so now that we've covered aneuploidy in the autosomes, the non-sex chromosomes, let's switch gears and focus on the sex chromosomes. We're going to look at 2 key examples that happen when you have an abnormal number of X or Y chromosomes, Klinefelter and Turner syndromes.
And here we have their karyotypes, side by side. Look at the left. For Klinefelter syndrome, you can count them up. There are 47 chromosomes in total, and the sex chromosomes are XXY. So there's an extra X. Now look at the right. For Turner syndrome, you see only 45 chromosomes in total, with just a single X. So you see the difference? One is a trisomy, the other is a monosomy.
Let's break down Klinefelter syndrome. This occurs in about 1 in 500 males, and it's also caused by that same non-disjunction mechanism, but this time of the X chromosomes. Because of that extra X, these individuals are male, but they often have features like sterility, testicular atrophy, and gynecomastia, which is breast development. A really important diagnostic clue here is that about 80% of cases will have a bar body. And if you remember, a bar body is that small, dense structure representing an inactivated X chromosome, something you wouldn't normally see in a typical XY male.
Okay, now for Turner syndrome. This one is incredibly high yield, so if you're taking notes, put a star next to this. It is the only monosomy that is compatible with life. That's a huge point. And even then, the vast majority, we're talking 98% of affected fetuses, are spontaneously aborted. For those who do survive, they have a female phenotype, and it's characterized by short stature, a webbed neck, and something called gonadal dysgenesis, which just means their ovaries don't develop properly, and that leads to infertility. Okay, so we've covered errors in chromosome number. Now let's talk about errors in chromosome structure. These kinds of abnormalities happen because of chromosome breakage, which is literally when a piece of a chromosome is lost.
This diagram shows you the core mechanism perfectly. You've got environmental factors, maybe viruses or radiation, that can cause a physical break in a chromosome. When that piece detaches, it can get lost completely, and that results in a deletion of all the genetic information that piece was carrying.
A classic textbook example of a large-scale deletion syndrome is Cri-du-chat. This is caused by a partial deletion of the short arm of chromosome 5. And the name? It's French for cry of the cat, and it comes from the most distinctive feature. Infants with this syndrome have a really high-pitched, cat-like cry. This is accompanied by microcephaly, severe intellectual disability, and pretty often congenital heart disease.
Okay, let's dive into something a bit more subtle, but incredibly important: microdeletions. These are smaller, contiguous gene deletions, and they introduce us to this absolutely fascinating concept of genomic imprinting. This is where it's not just what is deleted, but who you inherited it from, mom or dad.
Now, pay close attention because this slide is absolutely crucial. For some genes in our DNA, only one of our two copies, either the one from mom or the one from dad, is actually switched on. That's imprinting. So look at chromosome 15 here. If a specific microdeletion happens on the copy you inherited from your father, you get Prader-Willi syndrome. But if the exact same microdeletion happens on the copy you got from your mother, you get a completely different condition, Angelman syndrome. Isn't that wild?
And just look at how different these two syndromes are. Prader-Willi, which comes from the paternal deletion, is characterized by hypotonia, obesity, and hypogonadism. Angelman, from the maternal deletion, presents with severe motor and speech impairment and these unprovoked periods of laughter, which is why it's sometimes called the happy puppet syndrome. So you have two vastly different outcomes from the very same genetic loss. It all depends on which parent it came from.
All right, let's wrap up our tour of genetic errors with two final categories: fragile sites, which are specific points on chromosomes that are just prone to breaking, and then we'll finish with single gene mutations.
A key example here is Fragile X syndrome. It's caused by a fragile site on the X chromosome. To get a bit more specific, it's an expansion of a CGG trinucleotide repeat in a gene called FMR1. This expansion makes the chromosome unstable and, you guessed it, prone to breaking. This is a big one. It's the second most common cause of chromosomal intellectual disability, right after Down syndrome. And clinically, it often presents with features like large ears and a prominent jaw.
And finally, we're moving from these large-scale chromosomal problems to errors within the code of a single gene. These are single gene mutations. So while all the chromosomal issues we've discussed affect huge blocks of genetic material, these mutations alter the function of just one specific protein. They account for an estimated 8% of all human malformations and include a lot of well-known conditions like cystic fibrosis, sickle cell anemia, and Huntington's disease. And they all follow those classic dominant, recessive, or X-linked inheritance patterns you've learned about. Okay, wow, we have covered a ton of ground. Now it's time to lock in the most important, super high-yield information for your exams with a quick review. So let's focus in here.
This table right here, this basically boils it all down. For Down syndrome, you should immediately think trisomy 21 and those upward slanting eyes. For Klinefelter, think 47XXY, a sterile male with gynecomastia. Turner, that's 45X, the only viable monosomy. For Prader-Willi and Angelman, just remember chromosome 15. Paternal deletion leads to obesity, maternal deletion leads to that unprovoked laughter. And Fragile X is your number 2 cause of chromosomal mental retardation. Got it?
And let's just crystallize all of this with 5 absolutely crucial takeaways. 1. Non-disjunction is your main mechanism for aneuploidies. 2. Turner syndrome is the only viable monosomy. Can't say that enough. 3. Imprinting on chromosome 15 is all about which parent gave you that chromosome. 4. Always connect the genetics to the clinical picture. And 5. Understand the different scales of error, from a whole extra chromosome down to a single gene mutation.
And here's a final, really practical tip for your exams. The key here is pattern recognition. Learn to just spot the abnormal karyotype visually, whether it's trisomy 21, XXY, or 45X, and immediately link it in your mind to 1 or 2 unforgettable clinical signs. That connection is exactly what they're testing you on.
So, we'll end on this thought. Seeing how a single microscopic error, one extra chromosome, one tiny deletion can so profoundly alter the entire course of a human life, well, it's a powerful lesson, isn't it? It really highlights the incredible, unbelievable precision that's required for normal development and the delicate balance that it all rests on.
Have you ever stopped to think about the incredible microscopic journey that creates the very cells responsible for new life? Well, today, we're going to dive deep into the story of gametogenesis. It's the fundamental process that forges sperm and egg, and in doing so, it really sets the stage for the very beginning of all of us.
So what exactly is gametogenesis? At its heart, it's this amazing biological process that transforms these precursor germ cells into the highly specialized male and female gametes, the spermatozoa and the oocytes. It's all about getting them ready for that crucial moment of fertilization. So here's our game plan. We're going to start with the common ancestor of all gametes, these things called primordial germ cells.
Then, we'll take a quick detour into a really fascinating clinical topic, teratomas, before we explore the two very different paths, oogenesis for the female gamete and spermatogenesis for the male. We'll wrap it all up by comparing these two and hitting some key clinical notes.
Every story has a beginning, right? And for both sperm and egg, that beginning is the primordial germ cell, or PGC for short. You can think of these as the embryonic ancestors of all future gametes.
Now here's the really wild part, the journey these PGCs take. You'd think they'd start out in the gonads, but nope. They first show up way over in the wall of the yolk sac, around the 4th week of development. From there, they have to go on this incredible migration, kind of moving like little amoebas, all the way to the developing gonads. They have to get there by the end of week 5, and let me tell you, this journey is absolutely crucial for future fertility.
So this migration has to happen with incredible precision. But you know, in biology, things don't always go according to plan, which brings us to a really important clinical correlation. So what happens when some of these super powerful pluripotent cells, and remember, these are cells that can become almost any tissue type, what happens when they stray from their path? Well, the result can be something called a teratoma, like the one you see here. And these tumors are just remarkable because they are literally a jumble of different tissues. I mean, you can find hair, muscle, bone, even teeth inside. It's all because these misplaced pluripotent cells are just expressing their huge developmental potential, but in totally the wrong place.
This really explains where these things come from. The main theory is that teratomas come from these pluripotent PGCs that just wandered off their designated path. There is another idea that maybe they arise even earlier, from epiblast cells during gastrulation. But either way, it's a developmental mistake involving cells that have an immense amount of potential.
All right, so assuming that PGCs arrive safely where they're supposed to be in a developing ovary, we now get to follow their fate in a genetic female. This is the process of oogenesis, and believe me, it is truly a lifetime in the making.
The timeline is one of the most unique things about oogenesis. There's a ton of activity before birth. The PGCs multiply and enter the first meiotic division. But then, everything just stops. At birth, every single potential egg cell, which we now call a primary oocyte, is just sitting there, arrested on prophase 1. That's the very first stage of meiosis. The whole process only picks back up at puberty, moving forward in monthly cycles, only to pause again in meiosis 2, just waiting for fertilization to finally finish the journey. And to give you a sense of the scale here, get this. By the 5th month of fetal development, the number of germ cells in the ovary peaks at a staggering 7 million. From this point on, though, most of these cells are actually programmed to die off. It's a process called atresia. This massive die-off is exactly why the ovarian reserve is finite, and it's what sets up the biological clock for female fertility.
What you're seeing here is the state of the ovarian cortex right at birth. Each one of those surviving primary oocytes is stalled out in prophase 1 of meiosis. And importantly, each one is now wrapped in a single layer of flat epithelial cells, forming a little structure called a primordial follicle. This collection of follicles is literally the entire ovarian reserve a female will have for her entire life. Okay, let's fast forward to puberty. Each month, a small group of these primordial follicles gets recruited to start growing. As you can see here, those surrounding flat follicular cells start to get bigger and become cuboidal, and they multiply. This transforms it into what we call a primary follicle. At the same time, the oocyte and these follicular cells secrete a layer of glycoproteins, forming the zona pellucida, which is a really critical protective barrier.
As the follicle keeps on developing, these little fluid-filled spaces start appearing, and then they all merge together to form one big fluid-filled cavity called the antrum. The follicle is now called a vesicular or antral follicle, and at the same time, the surrounding tissue organizes itself into 2 layers, the theca interna, which is a vascular and hormonally active layer, and the theca externa, which is more of a fibrous outer capsule. Now, this is the big moment. Right before ovulation, there's a huge surge in luteinizing hormone, or LH, and that's the signal for the final maturation step. This hormone surge causes the primary oocyte to finally complete meiosis 1. But look at this division. It's completely unequal. One cell, the secondary oocyte, gets to keep almost all of the cytoplasm. The other one becomes this tiny non-viable thing called the first polar body. The secondary oocyte then immediately kicks off meiosis 2, but it arrests again, this time in metaphase, just waiting for a sperm to show up. Okay, let's completely switch gears and explore the male pathway, spermatogenesis. And wow, the contrast with oogenesis could not be more different. This is a continuous, high-volume manufacturing process that starts at puberty and just keeps on going, for life.
This comparison really nails the core differences, doesn't it? Oogenesis starts before birth, it's finite, and it gives you one huge ovum from each starting cell. Spermatogenesis kicks off at puberty, it's continuous, and it churns out 4 functional spermatozoa from each primary spermatocyte.
Okay, let's trace this lineage slowly, step by step. At puberty, the PGCs give rise to spermatogonial stem cells. These divide to make type A spermatogonia, which are basically a self-renewing stem cell supply. Then, some of those type A cells make type B spermatogonia. These type B guys are committed. They divide by mitosis to become primary spermatocytes. These are the cells that enter meiosis I, producing 2 secondary spermatocytes. Then those secondary spermatocytes really quickly finish meiosis II, and the result is 4 equal-sized but still round and immature cells called spermatids.
But hold on, a round spermatid is not a spermatozoan. It can't swim, it can't fertilize anything. To become a functional gamete, it has to go through this dramatic physical transformation called spermiogenesis. And this isn't cell division, this is a complete cellular makeover.
Spermiogenesis has 4 key events. First, you get the formation of the acrosome. Think of it like a little enzyme-filled helmet that forms over the nucleus, essential for getting into the oocyte. Second, the nucleus condenses like crazy, becoming super compact and streamlined. Third, the neck, middle piece, and tail are built. That middle piece gets packed with mitochondria to act as the engine for the tail. And finally, almost all of the extra cytoplasm is just shed, making the sperm lightweight and ready to swim.
Okay, let's bring both of these incredible pathways together now for a final summary and to look at a few key clinical points.
This table is the perfect summary. Notice those 2 major meiotic arrests that are unique to oogenesis compared to the non-stop process in spermatogenesis, and really focus on cytokinesis, the splitting of the cytoplasm. It's totally unequal in oogenesis to create 1 giant nutrient-packed cell, but it's perfectly equal in spermatogenesis to create 4 small, fast-moving cells.
And finally, just a quick clinical note. Given that about 300 million sperm are produced every single day, it's really not surprising that some are going to be defective. Up to 10% can have issues with their size, the shape of their head, or their tail structure. But the good news is, most of these abnormal sperm just can't swim properly, so they're generally unable to make it all the way to fertilize an oocyte. And that brings us to our final big question. We've seen these 2 totally different strategies for creating gametes, one that makes a single precious oocyte each month, and the other that makes hundreds of millions of sperm daily. It just begs the question, how does the body choreograph this meeting with such incredible precision that only 1 sperm fertilizes 1 egg to start a new life? Well, that is the story for our next explainer.
All right, let's dive into one of the most incredible journeys in all of biology, the very first week of human development. We're going to cover everything from the hormonal signals that get the ball rolling, all the way to the moment of fertilization and the very first cell division. It's an absolutely amazing process of precision, so let's get right into it.
So here's our roadmap. We're going to break this down into 5 parts. First up, we'll look at the hormones controlling the ovarian cycle. Then we'll zero in on ovulation itself. After that, we'll get into the nitty-gritty of fertilization, see what happens right after, and we'll wrap up by touching on some important clinical stuff you should know.
Okay, first things first. Before we can even really talk about ovulation, we have to understand the monthly cycle that makes it all possible. And it is all run by a really sophisticated hormonal command and control system.
Check this out. This image shows you the chain of command perfectly. It's a top-down system starting right in the brain with the hypothalamus. That sends a signal to the pituitary gland, and the pituitary, in turn, releases these hormones called gonadotropins, which then travel down to the ovary to manage the whole show.
So let's meet the key players. The hypothalamus kicks things off with gonadotropin-releasing hormone, or GnRH. That's the signal to the anterior pituitary to release 2 major hormones. You've got follicle-stimulating hormone, or FSH, and its name pretty much tells you what it does. And then you have luteinizing hormone, or LH. Now, LH is the real star when it's time for ovulation.
So once FSH is on the scene, a whole group of these primordial follicles starts to mature. You can see the changes right here. The main oocyte gets bigger, and it gets surrounded by more and more of these granulosa cells. Then you get these layers called the theca interna and externa. And finally, see that fluid-filled space? That's the antrum, and its appearance means we've officially got a secondary follicle. Now, here's a really crucial point. Even though FSH gets about 15 to 20 follicles to start this journey each cycle, it's a competition. Only one of them is going to become the dominant, or Graafian, follicle that actually gets to ovulate. It's basically the one that wins the hormonal race by being the most sensitive to FSH. All the others, they just degenerate. So all of that development builds up to the main event of the follicular phase, the moment of ovulation, when that chosen oocyte is finally released.
So what's the trigger? What's the final go-ahead signal? It's this, the LH surge. Right around the middle of the cycle, there's this massive, dramatic spike in LH levels. This surge is the one non-negotiable trigger that starts the whole process. If you don't get the surge, ovulation just doesn't happen. It's that critical. And this LH surge does three incredibly important things. First, it gives the oocyte the final push to complete its first meiotic division and start the second one. Second, it ramps up the pressure inside the follicle until it literally ruptures, releasing the oocyte. And third, it tells the leftover follicular cells to switch gears and start producing progesterone.
This picture just captures that moment perfectly. You can actually see the follicle has ruptured on the surface of the ovary, the oocyte is pushed out, and then these finger-like things called fimbria at the end of the uterine tube sweep it up and bring it inside to start its journey.
So what is it that's actually been released? Well, it's not just a simple cell. It's a secondary oocyte that's been paused or arrested right in the middle of its second meiotic division. And it's not alone. It's protected by this tough outer shell called the zona pellucida, and then even outside of that, there's a layer of cells called the corona radiata.
This diagram gives us a fantastic close-up. In the center, you've got the nucleus and the cytoplasm. Then as you move out, you can see that really important zona pellucida. And finally, that outermost layer of corona radiata cells. Any sperm that wants to be successful has to make its way through all of those barriers.
And here's a quick clinical aside for you. This whole process isn't always silent. That physical stretching and rupturing of the ovarian wall can actually cause a mild, one-sided pain. It's called Mittelschmerz, which is just German for middle pain. Pretty straightforward.
Okay, so the oocyte is now in the uterine tube. The stage is set for the next absolutely critical event, fertilization, which is the fusion of the male and female gametes. This slide basically gives you the full travel itinerary. After ovulation, the egg makes its way into the fallopian tube. And it's right here, in this wider section called the ampullary region, that fertilization is most likely to happen. That's the meeting spot.
Now here's a super important point. Sperm aren't ready to fertilize an egg right away. They actually have to go through a two-step prep course inside the female reproductive tract. These steps are called capacitation and the acrosome reaction.
Let's look at that first step, capacitation. This is a conditioning period that takes about 7 hours. During this time, the female tract basically activates the sperm by stripping a glycoprotein coat off its head. You can think of it like taking a safety cap off. It makes the sperm fully functional and ready for action.
And this diagram shows that transformation perfectly. On the left, that's the sperm as it arrives with its protective coat on, but after interacting with the female tract, that coat is gone. And on the right, you have a fully capacitated sperm. It's fertile and ready for the next step. So, once a single, capacitated sperm makes it all the way through and penetrates the oocyte, a whole cascade of irreversible changes begins. This is really the true start of a new individual. Fertilization accomplishes 3 huge things. First, it restores what we call the diploid number of chromosomes. Basically, it brings the 23 from the egg and the 23 from the sperm together to make the full set of 46, the complete genetic blueprint. Second, it determines the sex of the embryo. If the sperm carried an X, it's XX, female. If it carried a Y, it's XY, male. And third, it provides the spark to kickstart cleavage, which is just the first series of rapid cell divisions.
But you have to remember, this is all incredibly time-sensitive. The clock is ticking. If fertilization doesn't happen, the oocyte has a very short shelf life. It's only viable for about 24 hours after ovulation before it starts to degenerate.
And that brings us to our last section. We've seen how all these intricate steps have to line up perfectly. So, what happens when something goes wrong? Well, any disruption can lead to problems with conceiving, which is what we call infertility.
Now, infertility isn't a one-sided issue. It can come from factors in either partner. On the male side, common problems are things like not having enough sperm or the sperm not being able to swim well. For females, the causes can be anything from blocked uterine tubes, which can happen from things like pelvic inflammatory disease, to problems with ovulation or even an immune response against the sperm.
And just to put some numbers on the male factor, a count of around 20 million sperm per milliliter is generally seen as the lower end of the fertile range. A normal count can be way higher, even up to 100 million per milliliter.
You know, when you take a step back and look at the whole sequence, from a tiny hormonal pulse in the brain all the way to 2 cells fusing into one, it is just a stunning biological cascade. It really highlights the unbelievable complexity and precision that's required just to begin a new life. It makes you think, what else does this teach us about the amazing complexity hidden inside our own biology? Thanks so much for watching.
All right, today we're going to dive into one of the most remarkable transformations you'll ever see in biology. The very first week of human development. It's this incredible story of speed and, honestly, just mind-blowing precision. We start with a single cell that multiplies and organizes itself into a complex little structure, all ready for the next phase of its journey. So let's see how this all unfolds.
So here's our roadmap. We're going to start by looking at the big picture of human development, just to get our bearings. Then, we'll zoom right into week 1. We'll trace the embryo's path from the moment of fertilization through these super-fast divisions called cleavage and compaction, all the way to the formation of the blastocyst, and we'll wrap up with how it prepares for implantation. Believe me, it is a packed week of some incredible changes.
This really gets to the heart of it, doesn't it? This is the central question of all embryology. How in the world does a single, solitary cell become, well, us, a whole multicellular body? It's a question that takes us right into this beautifully orchestrated biological process.
The answer, it boils down to 3 fundamental processes working together. First, you've got growth. That's just a rapid increase in the number of cells. Then there's morphogenesis, which is the really cool part where these cells start organizing into a coherent shape and structure. And finally, differentiation, where the cells start to get their jobs, becoming specialized for specific functions. These 3 things are the engine driving everything we're about to see.
Okay, so keeping those core ideas in mind, let's get our bearings. Before we really zero in on that first week, it's super important to understand where it fits into the broader timeline of development.
So human development is typically broken down into 3 main periods. You've got the pre-embryonic, the embryonic, and the fetal periods. Our focus today is right at the very, very beginning, the start of that pre-embryonic period, which totally sets the stage for everything that's to come.
And here we are, day 0. This is the moment it all kicks off, fertilization. This single event is basically the starting gun for this incredible developmental race that we're about to follow.
Now, this diagram is great because it highlights the crucial geography of these early events. So, after the oocyte is released, it travels to a very specific part of the fallopian tube called the ampulla, and that's where fertilization almost always happens. The brand new zygote then begins its journey to the uterus, and its target is the posterior wall, which is the best spot for implantation.
Okay, our zygote is formed. What's next? Well, the next crucial phase begins right away. This is a period of just insane growth, and it's defined by 2 key processes, cleavage and compaction. So, what do we mean by cleavage? It's a series of mitotic divisions, but there's a really unique twist. The cells that are produced, which we call blastomeres, actually get smaller and smaller with each division. Why? Because the whole embryo is stuck inside the shell, the zona pellucida, which keeps it from getting any bigger overall. So about 30 hours or so after fertilization, that zygote undergoes its very first division. And the result, as you can see right here, is a 2-cell embryo. Each of those cells is a distinct blastomere. And the process just keeps going. The cells just keep doubling. 2 becomes 4, 4 becomes 8, and so on. But all the while, the cells themselves are shrinking, all still packed neatly inside that zona pellucida.
Now, right after the 8-cell stage, something pivotal happens. It's called compaction. The blastomeres, which were kind of loosely arranged, now huddle together and form these really tight junctions. And this is way more than just a physical change. It's the very first step in creating 2 distinct populations of cells, an inner group and an outer group.
You can really see the difference here. I mean, look, before compaction, the individual blastomeres are pretty distinct, almost like a little bunch of grapes. But after compaction, they form this smooth, tight sphere, and you can barely even make out the individual cell outlines. It's a really dramatic and absolutely crucial transformation. This physical change is also mirrored by a major shift in what these cells can become. See, before compaction, the cells are what we call totipotent.
That means each one has the potential to become any cell type, including the placenta. But after compaction, the inner cells become pluripotent. They can still form pretty much any cell type in the body, but not the placenta. This is our first major step in differentiation.
So, with this newly compacted ball of cells, the embryo is ready for its next big makeover. It's going to first form a morula, and then it's going to develop a cavity inside, becoming what we call a blastocyst.
By about day 4, we have a 16-cell embryo, and we call it a morula. It comes from the Latin word for mulberry because it kind of looks like one. And by now, those 2-cell populations are clearly defined. You've got the inner cell mass, which will become the actual embryo, and the outer cell mass, which forms the trophoblast, a really key component of the placenta. So how does this solid little ball, the morula, turn into a hollow blastocyst? Well, as it enters the uterus, fluid starts to seep through the zona pellucida, and it collects inside the inner cell mass. This fluid eventually all comes together to form a single cavity called the blastocele. And at that point, boom, our embryo is officially a blastocyst.
This diagram really lays it all out. You can see the key parts of the blastocyst here. The inner cell mass, which we now call the embryoblast, is kind of pushed off to one side. The outer cell mass forms the wall. That's the trophoblast. And then you have that big, fluid-filled blastocyst cavity. The whole thing, you'll notice, is still inside the zona pellucida.
And now we've reached the final stage of this crazy first week. The blastocyst has made it to the uterus, but to survive, it has to do 2 things: break out of its shell and attach to the uterine wall.
So around day 5, the blastocyst actually hatches. It breaks free from the zona pellucida. This is a non-negotiable step. Without this, the embryo can't grow any bigger, and more importantly, it can't make contact with the uterine wall to implant. And then, by day 6, the blastocyst makes contact. The trophoblast cells, that outer layer, adhere to the uterine epithelium, and this marks the very beginning of implantation, a process that's going to anchor the embryo and create that vital link to its mother. As this is all happening, let's just pause and think about the numbers for a second. The entire product of conception, this whole thing we call the conceptus, is now made up of about 107 cells.
And this is the really stunning part. Of those 107 cells, only 8 of them are going to become the embryo itself. The vast majority, 99 of them, are dedicated to creating the support systems, things like the fetal membranes and the placenta. This tells you everything you need to know about the top priority at this stage: building a safe and nurturing environment.
And that really brings us to the end of the first week. And it reveals a powerful truth about development. Before you can build the baby, you have to build its home. With over 90% of the cells dedicated to just support, it's crystal clear that the #1 mission of this first week is to establish a secure foundation for the 9 months to come.
All right, welcome back. Today we're diving into one of the most critical and honestly elegant periods in all of embryology, the second week of development. It's a time of incredibly rapid and symmetrical changes. In fact, it's so perfectly organized that it's often called the week of 2s. Let's get into it.
So here's what we've got on tap. We're going to start right at the beginning of the week, looking at what happens from day 8. Then we'll see how the embryo starts building its own crucial life support system. After that, we'll see how everything gets finalized, wrap our heads around all the new anatomy with a really handy mnemonic, and then, most importantly, we'll connect it all to the real world of clinical practice. Okay, let's jump right in. The blastocyst has just finished implanting itself into the uterine wall. The welcome mat is out. Now the real work begins, organizing the embryo itself and everything it's going to need to survive.
So, on day 8, our first set of 2s makes an appearance. The inner cell mass, the part that will become the embryo, also called the embryoblast, it splits into 2 very distinct layers. You've got the upper layer of tall columnar cells, the epiblast, shown here in blue, and the lower layer of smaller cuboidal cells, the hypoblast, in yellow. Together, they form this beautiful 2-layered plate called the bilaminar disc. At the same time, the outer cell mass, the trophoblast, also divides into 2. It forms an inner layer of single cells, the cytotrophoblast, and this outer, sprawling, multinucleated mass called the syncytiotrophoblast. And hey, notice that little space starting to form inside the epiblast? That's the very beginning of the amniotic cavity. Moving on to day 9, let's focus on the embryonic pole. That's the side that's really burrowing into the uterine wall. Here, that syncytiotrophoblast is just growing like crazy, and these little empty spaces, or vacuoles, called lacunae, start to pop up inside it. This is so important it's called the lacunar stage. Meanwhile, on the complete opposite side, the aembryonic pole, cells from the hypoblast start migrating down. They crawl along the inside of the cytotrophoblast, and in doing so, they enclose what used to be the blastocyst cavity. This new structure they've created is now called the primitive yolk sac. Okay, so as we hit the middle of the week, the game changes a little. The focus shifts from just creating new cell layers to building the actual infrastructure, the plumbing and support systems that are absolutely essential for nourishing this rapidly growing embryo. Then, around day 11, this whole new layer of cells just appears. It forms a kind of loose, web-like connective tissue we call the extraembryonic mesoderm. It basically fills in all the space between the cytotrophoblast on the outside and the amnion and yolk sac on the inside. You can see how this new layer literally pushes the primitive yolk sac away from the wall, creating more room for everything to grow. And by now, the original entry point in the uterine wall is pretty much healed over. Now, day 12. This is a huge milestone. Seriously, this is a game changer. That invasive syncytiotrophoblast keeps digging deeper and deeper until it actually breaks through the walls of the mother's capillaries, which are called sinusoids. For the first time, maternal blood flows out of her vessels and floods into those lacunae we saw earlier. This one event establishes the very first primitive uteroplacental circulation. It's the first time the embryo gets a real lifeline to its mother for nutrients and oxygen. It's a massive step. All right, we're heading into the home stretch of week 2. Now we're going to see some major reorganizations that give us our final setup for the week, and it perfectly paves the way for the really dramatic stuff that's going to happen in week 3. So on day 13, the yolk sac basically remodels itself. A second wave of cells migrates down from the hypoblast and forms a brand new, smaller cavity right inside the old primitive yolk sac. This new one is the secondary or definitive yolk sac. As it grows, it kind of pinches off these big, useless chunks of the old yolk sac, which just float away and become what we call exocoelomic cysts. And while you're looking, notice 2 other new things. These little fingers of cytotrophoblast pushing into the syncytiotrophoblast, those are primary villi, and this thick band of mesoderm, which we call the connecting stalk. By day 14, all those little spaces that formed in the extraembryonic mesoderm have all merged together. It's like a bunch of small puddles combining to form one giant lake. And this massive new cavity is called the chorionic cavity. It completely surrounds the yolk sac and the amniotic cavity, with one exception, that connecting stalk we just saw. That stalk is the only thing anchoring our little embryonic disc complex to the wall of the trophoblast. And, you guessed it, that stalk will eventually become the umbilical cord. Whoa, okay, that was a whirlwind trip from day 8 to 14, right? So let's pause for a second and put it all together using that fantastic mnemonic I mentioned at the start, the week of 2s. This week of 2s mnemonic just makes everything so much easier to remember. Let's run through it. First, the trophoblast splits into 2 layers, the syncytiotrophoblast and the cytotrophoblast. Easy enough. Second, the embryoblast splits into its 2 layers, the epiblast and the hypoblast. Got it. Third, 2 major cavities are formed, the amniotic cavity and the yolk sac. And finally, that extraembryonic mesoderm we saw also splits into 2 layers, creating that huge chorionic cavity between them. See? It's a really powerful way to keep all these key events straight in your head. You know, with all these new sacs and cavities popping up, it's easy to get them mixed up. So let's break them down one by one, just to be crystal clear. The amniotic sac forms from a space opening up inside the epiblast. The primitive yolk sac is just the old blastocyst cavity, but now it has a new lining made of hypoblast cells. The secondary or definitive yolk sac forms inside that primitive one. And finally, the biggest one of all, the chorionic cavity, also called the extraembryonic column, that one forms from all those little spaces merging together within the extraembryonic mesoderm. So here's the final picture at the end of week 2. The whole thing is now fully implanted in the uterus. We have our neat little bilaminar disc made of the epiblast and hypoblast. It has its 2 personal cavities, the amniotic cavity on top and the definitive yolk sac down below. And this entire precious package is just floating, suspended by that connecting stalk right in the middle of the huge protective chorionic cavity. Okay, so why do we need to know all this intricate day-by-day detail? Well, because this week is incredibly delicate. When things go wrong during these 7 days, the consequences can be profound. Let's look at some really important clinical examples.
You remember that syncytrophoblast we talked about? The one that's so aggressive? Well, it's not just a demolition expert, it's also a tiny hormone factory. It pumps out a hormone called human chorionic gonadotrophin, or HCG. This hormone is absolutely vital for keeping the pregnancy going. And here's the cool part. By the end of this second week, the HCG levels are high enough that we can actually detect them in the mother's blood or even her urine. And that, right there, is the biological secret behind pretty much every pregnancy test on the market today. Now, implantation doesn't always happen in the perfect spot. If the blastocyst implants somewhere outside the main body of the uterus, and the most common place for this is in the fallopian tube, it's called an ectopic pregnancy. This is a true medical emergency and is life-threatening. On the other hand, if implantation happens way too low in the uterus, so low that it covers the opening of the cervix, that condition is called placenta previa. This can lead to very dangerous bleeding later in pregnancy and almost always means the baby has to be delivered by C-section.
I want you to look at this number for a second. 50%. That's a staggering figure. This is roughly the percentage of all fertilized eggs that are lost naturally, often because something goes wrong in this incredibly complex dance of implantation and early development we've just been talking about. Let's break that down. So, to put that 50% number into context, a huge number of these losses happen before a woman even realizes she's pregnant. Now, if we look at pregnancies that are actually diagnosed by a doctor, about 15% of those will end in a miscarriage. And for a small but very significant group of women, about 1%, they suffer from the heartbreak of recurrent miscarriage, which is defined as 3 or more in a row. It just goes to show how incredibly vulnerable and complex this early period of life truly is. All right, if you're studying for an exam, these are the absolute high-yield points you have to nail. 1. Know the week of 2's mnemonic inside and out. 2. Remember day 12 is the day uteroplacental circulation begins, a huge deal. 3. Connect the syncytiotrophoblasts to HCG in pregnancy tests. 4. Be able to picture that final day 14 structure in your mind's eye. And 5. You absolutely have to know the difference between an ectopic pregnancy and placenta previa. And a quick tip for your practicals, get comfortable with the diagrams. You should be able to look at an image from day 8, 9, 12, or 14 and label all the key parts. For written exams, a classic question is to ask you to trace the origin of a cavity, like the amniotic sac, all the way back to its precursor cells. Knowing those pathways shows you really get it. And that brings us to the end of an incredible week. The stage is perfectly set. We have this beautiful, symmetrical, 2-layered disc floating in a sac. It's elegant, sure, but it's still just a flat disc. So the big question is, how on earth does this simple little plate transform into a complex, 3-dimensional body with a head and a tail, a front and a back? Well, the answer to that lies in week 3, with a spectacular process called gastrulation.
You know, the third week of human development is just incredibly transformative. In just 7 short days, a simple 2-layered disc completely reorganizes itself into a complex 3-layered structure. And this isn't just a small change. This is the moment we lay down the fundamental blueprint for every single organ and tissue in the body. Okay, so let's dive in and see how this incredible architectural feat actually happens.
So in this explainer, we're going to walk through the 5 critical stages of this week. We'll start with why it's so important overall. Then we'll break down the main event, which is gastrulation, and follow that with the formation of the super important notochord. After that, we'll take a look at the resulting 3-layered embryo, and finally, touch on why this is such a sensitive period from a clinical standpoint.
All right, first up, let's set the stage. Why all the fuss about the third week? What makes it so monumentally important in the journey from a single cell to a whole person? Well, it's because this week kicks off the embryonic period, a time of unbelievably profound and rapid change.
So that third week launches us into the embryonic period, this critical window that lasts all the way until week 8. This is the time frame when all the major structures and organ systems get laid down. We're talking the heart, the brain, the skeleton, the whole shebang. It's a period of incredible construction, but it's also the most perilous time for the developing embryo. It's just highly, highly vulnerable to any kind of disruption.
Now, the headline event of the third week is a process called gastrulation. And this is not just some minor adjustment. This is the major architectural phase that establishes the entire body plan. It's a real game changer.
So what is gastrulation really? Well, simply put, it's the transformative process where that 2-layered embryo reorganizes itself into 3 totally distinct foundational layers. We call these the primary germ layers, the ectoderm, the mesoderm, and the endoderm. And get this, every single tissue and organ in the adult body will come from one of these 3 layers. This whole process turns the embryo from a simple bilaminar or 2-layer disc into a much more complex trilaminar disc. So we start with 2 layers. You've got the upper epiblast and the lower hypoblast. But after gastrulation, boom, we have 3. The ectoderm on top, the endoderm on the bottom, and the brand new mesoderm sandwiched right in between. So how does this amazing transformation actually get started? Well, the very first visible sign of gastrulation is something called the primitive streak. It shows up as this narrow groove on the surface of the epiblast. Its formation is absolutely crucial because it defines the main axes of the embryo, head to tail and left to right. And this electron micrograph here gives us a fantastic real-world view of it. You can clearly see that primitive streak, and right at its cephalic end, or head end, there's a slightly raised area we call the primitive node. This whole structure is basically the gateway for cells to start migrating inward.
Okay, let's break down this inward movement, which is called invagination, step by step. First, epiblast cells start moving toward the primitive streak. When they get there, they change shape, becoming kind of flask-like, and then they detach from the epiblast layer. After that, they just slipped right underneath in this invagination movement. And it's these very cells that are going to form our new layers.
So here's the crucial part. What happens to those original layers? Well, the epiblast is the absolute star of the show. It gives rise to all 3 of the new germ layers. Some epiblast cells dive down through the streak and actually push the hypoblast out of the way, forming the new endoderm. Others slide in between the top and bottom layers to create the mesoderm. And the epiblast cells that just stay put on the surface, they become the ectoderm.
And here's what we get as a result. 3 distinct layers, all stacked together. You have the outer ectoderm, the middle mesoderm, and the inner endoderm. This 3-layered, or trilaminar structure is the fundamental blueprint that the entire body is going to develop from. It's all right here.
As more and more cells keep migrating through that primitive streak, they start to spread out. They move both laterally, off to the sides, and cephalad, towards the head. The new mesoderm layer just spreads out between the ectoderm and endoderm, acting exactly like the filling in a sandwich.
But there are 2 really important exceptions to this spreading. At the cranial end, the head end, the ectoderm and endoderm stay fused together at a spot called the oropharyngeal membrane. This is going to become the future mouth. And then similarly at the caudal or tail end, they stay fused at the cloacal membrane, which marks the spot of the future anus.
So, while all of this gastrulation is happening and creating the 3 layers, there's another critical process going on at the same time, and that is the formation of the notochord, the structure that's going to define the central axis of the entire embryo. The notochord forms in this really precise sequence. First, a special group of cells, the prenotochordal cells, they dive inward right at the primitive node and migrate straight forward along the midline toward the head. They actually integrate themselves right into the endoderm layer for a bit, forming a temporary thing called the notochordal plate. Then finally, these cells detach from the endoderm and come together to form a solid, rod-like cord, and that's the definitive notochord.
So why is this little rod so important? Well, it's got 3 massive jobs. First, it defines the primary body axis, which gives the embryos bilateral symmetry. Second, it serves as the foundation for the axial skeleton. That's our future vertebral column. And third, and this one is just so critical, it acts as a primary signaling center. By releasing specific molecules, it basically tells the ectoderm above it to thicken up and form the neural plate, which is the very first step in building our brain and spinal cord.
So, at the end of all this migrating and invaginating and inducing, what do we actually have? Well, we have a fully formed trilaminar embryo, and it is packed with incredible potential.
This cross-section right here shows the whole picture at the end of week 3. You can see the ectoderm on top, the endoderm on the bottom, and the mesoderm layered right in between. And sitting in the midline, just below the ectoderm, is our newly formed notochord. The whole thing is flanked by the amniotic cavity above and the yolk sac below. All the key players are now in position, ready for the next critical stage, organogenesis.
And now, organogenesis, the formation of organs, can really kick into high gear. Each germ layer has a very specific and distinct job to do. The outer ectoderm is destined to form our skin and our entire nervous system. The middle mesoderm is going to build our muscle, bone, blood, and the heart. And that inner endoderm creates the lining of our digestive and respiratory tracts, including things like the lungs.
Okay, let's connect all this amazing biology to why it matters clinically. Understanding these steps is so crucial because when they go wrong, the consequences can be incredibly severe.
Here's a pretty simple way to remember the key outcomes of this week, a little mnemonic sometimes called the Week of Threes. We've now established our 3 primary germ layers, ectoderm, mesoderm, and endoderm, and the embryo itself is now clearly organized around its key cavities, mainly the amniotic cavity and the yolk sac.
This summary diagram really puts all those pieces together nicely. You can see that 3-layered or trilaminar embryo right there in the center. It's surrounded by all its essential support structures, like the amnion forming the amniotic cavity and the yolk sac down below. It's a highly organized system, now totally primed for the explosive growth of organogenesis.
And this brings us to what might be the most critical clinical takeaway of all. Because gastrulation establishes the entire body blueprint, this period is extremely sensitive to what we call teratogens. A teratogen is any substance like high doses of alcohol or certain drugs that can disrupt development and cause birth defects. An error during this foundational stage won't just affect one little part, it can have absolutely devastating, cascading effects across multiple interconnected organ systems.
So let's end with a question for you to think about. Considering that the primitive streak is the gateway for forming both the mesoderm and the endoderm, how might a disruption in its function completely derail the development of an entire organ system, like the cardiovascular or digestive system? This link between a fundamental process and its clinical outcome is really at the very heart of what embryology is all about.